Hello everyone again, this
is
Ismail Badran, your instructor for Chemistry 101, and today we're going to continue with this chapter 5, gases chapter. So let us recall what happened in what we talked about in the previous lecture, Boyle's and Charles and Avogadro's law. Laws, they all combined into the ideal gas equation, which was PV is equal to nRT. So this ideal gas equation is actually the result of the experimental work of these three scientists. We also proved that P1 V1 over T1 is equal to P2 V2 over T2 for a gas that is changing state from, let's say, state A to state B. We also now, so this is what I've been talking about in the previous slide. So now, what is an ideal gas equation? An ideal gas equation, it's an equation that describes what we call an ideal gas. Ideal gas is a gas that behaves ideally. It does not exist in nature. So some of the characteristics of this gas is like, first of all, the molecules, they don't attract or repel each other. So we assume that the assumption here is that the molecules, they don't actually repel or attract each other. So there is no repulsion or attraction forces. And the other thing is that the molecule size is too small. So we assume that the molecules have no size, and therefore the volume of the molecules is negligible compared to the volume of the gas. As I said, this gas actually, this ideal gas, most gases, they don't, in nature, in actual life, they don't behave as ideal gas. So they deviate from ideal gases. But in this chapter, we apply the ideal equation, for practical reasons. Now, we need to define something called STP. So STP is standard temperature and pressure. So that means we are at 0 Celsius and 1 atmosphere. So STP, again, it's standard temperature and pressure. So it's 0 Celsius, which is 273.15 Kelvin, and 1 atmospheric pressure. That's what we call STP. Under these conditions, if you have 1 mole of a gas, it should occupy 22.414 liter. Under the ideal gas behavior, or under the ideal gas theory, all gases should occupy this volume despite their nature. So if you have either nitrogen, hydrogen, whatever, 1 mole of a gas at 0 Celsius under 1 atmospheric pressure, its volume should be 22.414 liter. So you can use this number to calculate the R value actually at STP. So recall that PV is equal to RT. Therefore, you can rearrange this equation to become R is equal to PV or NT. So the P is 1 atmosphere times this volume, the one we talked about, 22.414, divided by N, which is 1 mole, times the temperature in Kelvin. So the 0 Celsius is 273.15 Kelvin. If you do the math, you will find R to be equal to this value, 0.021, roughly 1. The units is liter, atmosphere, mole, minus 1, Kelvin, minus 1. So this is the gas constant R and its units. Now, so this actually leads us to a very important result here, is that whatever the gas is, if you have helium, fluorine gas, argon gas, whatever, if you have 1 mole of each, and they are all under STP conditions, the volume of that gas should be equal to 24.2 liter, 22.4 liter. So despite the nature of the gas, that's ideal gas behaviors, and this will have an important application later in this chapter. Now, let's go back and just focus on these two equations that we talked about. The PV is equal to RT, and the P1 V1 over T1 is equal to the other side. We need to start applying real-life examples on these ones. Okay, so we have this question 5.3. We got sulfur hexafluoride, and the question is asking to calculate the pressure in atmosphere. And we have number of moles, which is 1.82 moles of the gas, and we have a volume of 5.43 liter at 69.5 Celsius. So I have just organized my data here. So the question is asking for the pressure, and we have a number of moles, we have a volume, we have a temperature that I have already transferred that into Kelvin. And it looks like this question can be solved by the PV and RT equation without any problems. We just need to have the R value. R is equal to 0.0821 atmosphere liter mole minus 1 Kelvin minus 1. So I'm just going to proceed with the answer here. PV is equal nRT. So I need the pressure. So the pressure is equal to nRT over volume. I just divided both sides of the equation by volume. I got this one. So in this case, the pressure is equal to the number of moles. And it's very important in these questions to put the units, because this will ensure that the units cancels out and you're doing the right thing. So we have 1.82 mole times R, which is 0.0821. And the units of R is atmosphere, liter, mole minus 1, Kelvin minus 1. Times the temperature. Now, if you put 69.5 Celsius, that's not good, because the Celsius does not cancel out. You must change that into Kelvin. Remember to change that into Kelvin. So 3.342 Kelvin, 0.65. We don't have to put that. And over the volume, which is 5.43 liter. Now, if you see here, everything cancels out nicely. So this liter goes with this liter. The Kelvin minus 1 goes with the Kelvin minus 1, and you have the mole here cancels out with this mole minus 1. So if you do the math, you will find the answer to be 9.4 atmosphere. So the pressure is equal to 9.4 atmosphere. We can practice this at home and make sure we get the right answer. Now, the other question is, ammonia gas is used as a refrigerant in the food processing and storage industries. Calculate the volume, so it needs the volume in liters occupied by 7.54 grams of ammonia at STP. So we don't have much information, we just have ammonia and grams, and he needs the volume. So I have organized my solution here. So question 5.4, we have 7.4 grams of ammonia. The molar mass of ammonia, this is something you have to calculate. The molar mass 17 grams per mole. And we have STP. So you need to know that STP means 1 atmosphere and 0 Celsius. Okay? And we need the volume. So again, to calculate the volume out of this information, you can apply the PV and RT, but you will find out the number of moles is missing. So the plan here is to calculate the number of moles and to go from number of moles into the PV and RT equation to find the volume. So if we know the number of moles, T is given, R is always given. We have the pressure, do we? Yeah, the 1 atmosphere. So we can calculate the volume. So let's proceed. So number of moles is equal to the 7.4, the mass divided by molar mass, of course, which is 7.4 grams divided by 17 grams per mole. That will give you an answer of 0.43 mole. So PV is equal to nRT. We're looking for the volume, which is again nRT over pressure, and that should be equal to the number of moles we obtained, which is the 0.43 mole, times R, which is 0.0821. I'm not gonna do the units here because I have done it before. So, but in your case, you should actually do the units in the exam. because you just need to know that everything cancels out. This is something. Now, times T, which is the temperature in Celsius, if you put 0, that will give you an answer of 0, and that's not good. So you must change again the temperature into Kelvin. 0 Celsius is 273 Kelvin, divided by the pressure, which is 1 atmosphere. So again, I'm not putting any units here, but you should put the units in any question that you are solving, and that should give you an answer which is 9.7 liter. This question has another solution. There is another solution for this question. Please look at the book and see how he's doing it. There's actually an easy one doing the. You can say at STP you have 22.4 liters, so you can do a proportion and resolve the question. Okay, so the next question is an inflatable helium balloon with a volume of 0.55 liter at sea level, so have a volume and a pressure, is allowed to rise to height of 6.5 kilometers, where the pressure is about 0.4 atmosphere. So the pressure is changing here, assuming that the temperature remains constant. Okay, that's important. What is the final volume? So this is kind of a question that you have a P and V, P1, V1, and he's asking about V2, okay? Giving that you have P2, but this 6.5 kilometers is misleading, okay? He's just giving that to mislead you. The 6.5 kilometers has nothing to do with this question. So this is example 5.5 from the book, and I have organized the information here. That I have V1 is 0.55 liter, and P1 is 1 atmosphere. We're asking for V2, and we have a P2. So you cannot use the PV and RT here because you don't have number of moles, and you don't have. It does not apply here. So the best thing is to use P1 V1 over T1 is equal to P2 V2 over T2, but temperature is constant, as the question says, and therefore the T1 is equal to T2, and they cancel out, and you will have a very nice equation, which is P1 V1 is equal P2 V2. Now we are been asking for V2, so in this case you can say V2 is actually P1 V1 over P1 V1 over P2. So let's double check here. He's asking for V2. Yes. So now we just plug in the numbers. So P1 is 1 atmosphere. Times V1, which is 0.55 liter, divided by P2, which is 0.4. In this case, you can see that the atmosphere goes with the atmosphere, and the answer will be in liter, which is what we want. And in these type of questions, there is no need to change the units. If the pressure is in atmosphere, if P1 and P2 are in atmospheres, you don't have to change them to anything else. If you are giving pressures, let's say in torr, you don't have actually to convert them into atmosphere, because they will cancel out. This is just like the dilution problem, if you remember from chapter 4, M1 V1 A equal to M2 V2. There is no need to change the units here, and you just plug in the numbers, and you will have an answer which is 1.37 liter. Now let's think about our answer. Does it make sense? So here we have a volume 0.55 liter at 1 atmosphere. I'm decreasing the pressure, so the volume should increase, and this is what happened. The volume increases to 1.3. So always think about the common sense of your answer, and does it make sense or not. Okay, so let's move on to the next example. Argon is an inert gas used in light bulbs to retard the vibrations of tungsten filament. So a certain light bulb containing argon at 1.2 atmosphere and 18 Celsius. So I've been given a pressure and temperature. Is heated to 85 Celsius. The temperature is changing. This is not a constant temperature. and at constant volume. Okay, that's nice. So this is at constant volume. Calculate the final pressure. So again, this is a type of question that you can use that equation, P1 over V1 over T1 equals this, and either it is constant temperature, constant volume, or constant pressure, or maybe everything is changing. But this is a situation where you have a constant volume. Let's see how we can proceed with this question. This is question number 5.6. So 5.6 is this. So P1 is 1.2 atmosphere. T1 is 18. I already changed it to Kelvin. That's very important to change this into Kelvin again. And I'm asking for P2 at another temperature. Now here, the volume is constant. So P1 V1 over T1 is equal P2 V2 over T2. But volume is constant, therefore the volume cancels out, and you have P1 over, did I make a mistake here? This is T1, sorry. Over T1 equals P2 over T2. So here I am been asking for P2, so you want to rearrange this. So P2 in this case, you have to be very careful when you do these equations. It's equal P1 times T2 divided by T1, which is equal, P1 is 1.2 atmosphere times the ratio of T2 over T1, so 358 Kelvin over 291 Kelvin. So this goes with that, and you will have the pressure P2 in terms of atmosphere, and P2 in that case will equal to 1.48 atmosphere. You can rethink about the answer and see if it does make sense. When you increase the temperature, what happens to the pressure? So recall that from the previous lecture, please. I will just leave this question as a homework for you to practice. I think this one is the one we change everything, the pressure and the volume and temperature. So can you practice that at home, please? Okay, one nice thing about the gases is that we can actually relate the PV and RT equation to the density of the gas. Now, the density of the gas or anything, it's mass over volume, so that's not changing. This is a rule in physics, and we refer to the density by the little Greek letter with rho. This is not P, this is rho. It's a Greek letter referring to density. So rho is m over v. So we have PV is equal in RT, and we have the number of moles equal mass over molar mass. You can play with these equations, and you come up to this equation here, which is PV is equal mass over molar mass RT. I just replaced the number of moles with m over m. And now I'm rearranging this. I'm trying to get the density inside. So I'm dividing both sides of the equation by volume. I get to this. P is equal mass over V molar mass RT. But we know that m over V is density, and therefore you have P is equal rho RT over m, and you can rearrange this and you come up to this equation. This is a very nice equation. Molar mass is equal rho RT over P. You should memorize this one. If you forget it, you can just derive it very quickly. It's not very difficult to derive this equation. Now, what's the application of that? The application of this is if you are able to measure the density of a gas, you can know its molar mass. So this is used to identify the molar masses of unknown gases, or vice versa. So we have some questions here in the book to apply this. The first one is that to calculate the density of carbon dioxide, CO2, in grams per liter at 0.9 atmosphere and 55 Celsius. So this question is question number 5.8. So 5.8 is this one. So P here the rho is missing. We can't find. He's asking about the density. CO2, so the molar mass is 44. We have calculated that many times. And pressure is 0.9 atmosphere. This is a pressure, this is density, please, okay? So this is a rho, and this is pressure. And temperature is 55, which is 328 Kelvin. So what do we have here? He's asking for the density. So you can just plug in this equation, which is M is equal rho RT over P. So M is equal rho RT over P. That means rho is equal, if you rearrange this equation, you should now be good in rearranging these equations and you get what you want. So it's MP, molar mass, times the pressure over RT. Now make sure that your pressure is in atmosphere, your molar mass in gram per mole, and R is in the units, the usual units, and temperature is Kelvin. From this you can get the density in units of a gram per liter. It's not gram per milliliter, it's gram per liter. So we'll proceed with that, and that will be equal 44 gram per mole times the pressure, which is 0.99 atmosphere over T. So we have MP over RT, so 0.0821, that's atmosphere liter, 1 minus 1, Kelvin minus 1, times temperature, which is a 328 Kelvin. It's very important in these questions to put the units, because you want to see if they cancel out or not. Let's see what we have here. This atmosphere goes with this atmosphere. This Kelvin goes with this Kelvin minus 1. And this mole goes also with this mole. So we are left with gram, which is this one, divided by liter, which is a good and if you do the math here with the calculator, you will find the answer to be 1.62. So 1.62 gram per liter for